Can you find a right triangle with area exactly 210 if every side must be a positive whole number? It sounds simple, but there are actually quite a few possibilities to check. Let's see if we can find all of them without testing every possibility one by one. Let the two legs be A and B, and let the hypotenuse be C. The area of a triangle is 1/2 times base times height. So 1/2 times A times B equals 210. Multiply both sides by 2, and we get A times B equals 420. Since A and B are integers, we just need the factor pairs of 420. Let's assume A is the shorter leg. The possible pairs are 1 and 420, 2 and 210, 3 and 140, 4 and 105, 5 and 84, 6 and 70, 7 and 60, 10 and 42, 12 and 35, 14 and 30, 15 and 28, and finally, 20 and 21. That gives us 12 possibilities. Testing all 12 with the Pythagorean theorem would be tedious, so let's find a shortcut. We know a squared plus b squared equals c squared. And because c is the hypotenuse, it must be larger than b. Since all the side lengths are whole numbers, we can write c as b plus n, where n is a positive whole number. Substitute that into the Pythagorean theorem. We get a squared plus b squared equals the quantity b plus n squared. Expanding the right side, we get a squared plus b squared equals b squared plus 2bn plus n squared. The b squared terms cancel, leaving us with a squared equals 2bn plus n squared. Factor out n, and we get our key equation. A squared equals n multiplied by the quantity 2b plus n. This gives us a very useful filter. Since n is at least 1, the smallest possible value of n times the quantity 2b plus n is 2b plus 1. Therefore, a squared must be at least 2b plus 1. And that eliminates a lot of our factor pairs immediately. For example, take 7 and 60. A squared is only 49, but 2b plus 1 is 2 times 60 plus 1, which is 121. 49 is much smaller than 121, so that pair is impossible. In fact, this simple inequality eliminates every pair up to 7 and 60. So now we only need to test the survivors. First, 10 and 42. A squared is 100. Our equation becomes 100 equals n multiplied by the quantity 84 plus n. There is no positive whole number n that works, so this pair is impossible. Next, 12 and 35. Now a squared is 144 and 2b is 70. So we have 144 equals n multiplied by the quantity 70 plus n. What if n equals 2? 2 times the quantity 70 plus 2 is 2 times 72, which is exactly 144. We have a winner! So the hypotenuse is b plus n, which is 35 plus 2, or 37. Therefore, our first triangle has side lengths 12, 35, and 37. Now let's keep going. Try 14 and 30. Our equation becomes 196 equals n multiplied by the quantity 60 plus n. no positive whole number n works, so that pair is out. Next, 15 and 28. We get 225 equals n multiplied by the quantity 56 plus n. Again, there is no positive whole number n that works, so that one is out too. And finally, 20 and 21. Here, a squared is 400 and 2b is 42. So we need 400 equals n multiplied by the quantity 42 plus n. Try n equals 8. 8 times the quantity 42 plus 8 is 8 times 50, which equals 400. Another perfect match. The hypotenuse is therefore 21 plus 8, which is 29. So our second triangle has side lengths 20, 21, and 29. And that's it. Out of all 12 factor pairs, only 2 produce integer right triangles. The 2 solutions are 12, 35, and 37. And 20, 21, and 29. Both have an area of exactly 210, and all 3 sides are positive whole numbers. Which one did you find first? Let me know.